All right, guys, so this is lesson 6.6, which is on page 301 in your Walsh book. So that's real. You guys have made it through 301 pages of Math 2 while you have been at home. So I'm so impressed by everything that you have done, and let's get through it. So on this question here, we've already been looking at thinking about whether events are independent or dependent when we have conditional probabilities, which is using the word given or if. And now we're going to be looking at events based on the word and sort of two things happening together. So the first question here is just sort of a review of what we've already talked about, because we know that when we have the word, or when we have replacement and without replacement, that's its own set of independent, dependent. So it's just making sure we know which one is which. So if we're looking here, it says for each experiment, decide whether getting red on the first pick and getting black on the second pick are independent events. So in experiment A, you are picking a marble, then you're putting it back, you're putting that marble back in the bag, then you're picking a second marble. In the second one, you're picking a marble from the bag, you are not replacing it, and then you're picking a second marble. So it's asking us for each experiment, we're talking about red first and then black second. So when it asks you to assign the variable names, it's just wanting you to put some sort of variable that's going to reference the situation. So our F here can be red first, and then BS can be black second. So for experiment A, it's trying to determine whether RF and BS are independent events. Well, we know that in experiment A, the first marble, so that red marble that they picked, would then be put back into the bag. So the probability, and like the way that you can think about this, and there's not really a rule for this, but the probability of that red marble being picked first is there's 2 out of 6. So the probability of the red being picked first here would be 2 out of 6. And then they're going to put the marble back in, and then the probability of the black being picked second would be 4 out of 6. So because we're able to determine each of those, we know we could find the probability by multiplying, and because it was replaced, they are independent events. So here it's telling us to determine whether red first and black second are independent events. Well, here red first would still be 2 out of 6. But now black second here, really the probability of picking the black second actually depends on what was picked first. Because here, of course, in this situation, we're assuming the red was picked first. But now we only have 5 marbles left, and there would be 4 out of 5 there. Now, here's the thing, though, is that this is an assumption that the red marble's picked first, that there would still be 4 blacks. It is possible that they don't pick a red marble first, right? And then you end up picking a black one. You have a black one in your hand, you're not putting it back. Well, then the probability here is actually only 3 out of 5, because that black marble wouldn't be there because you pulled it out. So in this situation, whether or not you pick the black marble second really does depend on whether or not you picked that red marble first, because whether or not you picked a red marble first has an effect on how many black marbles are left in the bag. Whereas in the first situation where you put it back, it doesn't really matter what you picked the first time, because the situation is replenished. It's exactly the same for the second time. But since for the first time, the actual number of black marbles left in the bag depends on what you picked the first time, these are not independent events. These are dependent events. And again, dependent is always going to be without replacement. And then independent is always going to be with replacement. So I hope that makes sense there. But that's it for that one. So when we're moving on to the next one, we're now looking at a situation where we are going to be able to analyze our A and B in the sample space. So we're actually going to be able to determine whether or not these are going to be independent or dependent based on a rule about both. So again, this is not given, this isn't conditional. It is still true that we have the probability of A given B would be equal to the probability of A for them to be independent. That's still true. The probability of B given A would be equal to the probability of B if they're independent. That's still true. But this is now talking about and. We're not talking about given anymore. We're talking about and. So when we are looking here, we're talking about a coin toss 3 times. So we know that when we have a coin toss 3 times, we have even odd. No, we don't. That would be called dice. Because coins don't have even and odds. They have heads and tails. And then they have heads and tails again. And the third time they still have heads and tails. So hopefully you are adept at making the sample space, or you have a nice one to return to. But that's our sample space, and there are 8 different outcomes. So what I've done here is I've actually gone through and listed the different outcomes here so that we can analyze them more quickly. So there is another independence rule that we are going to learn, which basically says that if events are independent of one another, that the probability of A and B, if they are independent, will be equal to the probability of A. That's fascinating. Will be equal to the probability of A multiplied by the probability of B. So if we're going to go to figure out whether these are independent events, there's information that we need to know. So let's first start just by listing the different probabilities that exist in this situation. So the probability of A, well, A is the first toss is heads. So the probability of A is going to be 1/2, or 4 out of 8, but 1/2. The probability of B says the second toss is heads. Well, the probability that the second toss is heads was 1, 2, 3, 4. So also 4 out of 8, so that's also 1/2. Then C says there are exactly 2 consecutive heads. Well, that's 3, so that doesn't count. That's 2 consecutive heads. That's 2 consecutive heads. So that's 2 out of 8, or 1/4 there. So those are the probabilities of A, B, and C. So now I'm going to get the probabilities of A and B. So A and B here is the probability that the first toss is heads and the second toss is heads. So that's this one here and this one here. So A and B looks like 2 out of 8 events, so that would be 1/4. Then A and C, well, A says the first toss is heads, and then there are exactly 2 consecutive heads, so that looks like only this one. So that's 1 out of 8. And then B and C, so B and C says the second toss is heads, and there are exactly 2 consecutive heads. So second toss is heads, 2 consecutive heads. Second toss is heads, 2 consecutive heads. So that's 2 out of 8, or 1/4. So those are the different probabilities that we're going to be working with here. Now, if we want to determine whether or not each of these events is independent or dependent, we just need to use our rules here. So the probability of A and B, according to the list that we just created, the the probability of A and B was 1/4. So if these are independent events, then A and B is going to be equal to A times B. Well, the probability of A was 1/2, and the probability of B was also 1/2. So here it says that 1/4 would be equal to 1/2 times 1/2, which is 1/4. So right now that tells us that these events are independent. So what that means is the first toss being heads has absolutely no effect on the second toss being heads. All right, which does make sense. It's two different coin tosses. All right. So in the second situation, we have the probability of A and C. So A and C was 1 out of 8. So I want to know if that's equal to the probability of A, which is 1/2 multiplied by the probability of C, which is 1/4. So that would be 1/8 is equal to 1/8. So that means that these are indeed independent events again. All right. And then the last one here is B and C. So it tells us B and C, our probability there was 1/4. Then the probability of B is 1/2, and the probability of C is 1/4. So 1/4 is equal to 1/8. That is not true. So what that tells us is that we are dealing with events that are dependent. So again, this is a rule that helps you analyze whether certain situations are independent or dependent, but only when we are using and. If you have a given situation, if you have a conditional probability situation, you are absolutely dealing with a situation where you have to use conditional probability independence dependence, which is up here. All right, so in example 3, we are applying the same information, but we've got a bivariate data table or a two-way frequency table here. And I guess this isn't technically a bivariate because it has 3 by 4, but it has 2 major categories. So I guess it is actually technically a bivariate data table. It's comparing variables about bread choice and sandwich choice. But here we go. So it is asking us to figure out some information here to determine whether they order a club sandwich on country white, so that's club sandwich and country white, and the roasted chicken on whole wheat, so that's roasted chicken and whole wheat. So it's basically asking us to analyze the event. So it's asking us to analyze club sandwich, so that's going to be CS. No, it's the Landon's club sandwich, so let's make it LC. And country white, CW. And then this one is going to be asking us to think about the probability of chicken sandwich. So let's make that RC, roasted chicken, and whole wheat, so WW. So those are the situations that we're going to be looking at here. So when we are dealing with a table like this, we need totals. So total club is 92, total turkey melt is 80, total roasted chicken is 75, roasted veggie delight is 73. Country white total is 102, whole wheat total is 112, and sourdough total is 106, and your total here is 320. So we found totals for all three categories. So we've got LC and CW for that first person here. And basically, we're trying to determine whether or not these are going to be independent events. So, what I need to know if they're going to be independent, I know that the probability of both will be equal to the probability of each multiplied by one another. So, the probability of LC is 92 over 320. So, for LC, I'm going to put 92 over 320. Then for CW, that's country white bread. That's 102 out of 320. Now, the ones that got both, country Landon's Club, so on the country white bread is going to be 44 out of 320. So basically, if what I'm trying to determine now is whether or not these are independent or dependent. So I'm going to give some decimal equivalents to these as we're working. So we're going to make our probability of the club. We're going to make that 0.2875 because I want to be pretty specific and I'm multiplying small values. Country white, we're going to make that 0.3188. And then for both, we'll make that 0.1375. So now if I want to determine if the events are independent, I want to see if they're equal. So the probability of both there is 0.1375, and that would be equal to the individual probabilities multiplied by one another. So when I multiply those two probabilities, I get about 0.0916, and here I have 0.1375. So I'm going to go no. I wouldn't start saying those are the same unless I had 0.139 or 0.13 something. So those are not the same, so we're going to say that these are dependent events. Ooh. And we're going to say lots of things I didn't mean to say there in that little box that built itself. Okay, moving on. These are dependent events. So we're just going to move on from that space that has built itself. All right, so again, not the same. So we're going to move on to the next part. It's asking us to think about just two different items here. So when I go to analyze the probabilities that I need here, the probability of RC, of the roasted chicken, that's 75 out of 320. The whole wheat is 112 out of 320. And then the probability of both, the chicken on whole wheat, was 26 out of 320. So now I'm going to try to determine whether or not these are independent events. So my decimal equivalent here is going to be about 0.2344. This is going to be about 0.35. This is going to be about 0.0813. So now I go to do some multiplication here. Well, the probability of both is 0.0813, and the probability of the roasted chicken was 0.2344 times 0.35. So when I multiply, I get that 0.0813 is equal to 0.0820, and I'm going to state that those are pretty much exactly the same there. So I'm going to state that these are much more like independent events. All right, so we are getting very close to being done here, but hang on because these next two are a little bit different. So for number 4, you've got the town cinema next to somebody. You've got 200 people who saw a movie and also ate at the bistro. So you've got the movie and the bistro. So the probability of the movie let's actually keep going before I get too excited. So so it said the survey indicated that 80% liked the movie, 60% liked the movie and their meal. So it wants me to assume that liking the meal and liking the movie are independent events, which makes sense because they're not really related. So it says based on the survey, what is the probability that the randomly chosen moviegoer will like a meal at Rhiannon's Bistro? So we know that the probability that they like both is 0.60. We also know that the probability that they like the movie is 0.80. But it tells us to assume that they are independent events. So if we assume that they're independent events, what that means is the probability that they like both will be the same as the probability that they like the movie multiplied by the fact that they like the dinner. So again, if I know that, I know that the probability of both is going to be equal to the probability of liking movie times the probability of liking dinner. So the probability of both in this question we already figured out was 0.6. We know the probability of liking the movie was 0.8, but we don't know the probability that they liked dinner yet. So in order to find this, all I have to do is get this probability by itself. So I need to divide by 0.8, and that gives me that the probability that they like the dinner is 0.75. And again, we can only do that because we are assuming that they are independent events there. So again, independent events. In independent events, you can multiply the two together to find the probability of both. All right, so last one here. So again, we're on page 303. So it says you got a basketball game. They've just had the score in the final seconds of the game. He's fouled, so he's got a free throw. Then the referee calls a technical foul on the other team, so you can get a second free throw attempt. So in a technical foul, the reason this question is so specific is you can choose who shoots the free throws. Often, most of the time, unless it's like assigned toward a specific player. But in this situation, it was like a team foul overall, whatever. So the other team, they get to pick who shoots the free throw. So the coach assigns a different player, Rico, to shoot the second free throw. So it tells us that Joel's made 32 out of 50 of his free throws, and Rico has made 42 out of 48. So wants to know what is the probability that Joel or Rico is going to make a free throw to win the game. So basically, Joel's going to get to shoot his, and then Rico is going to come shoot his as the second free throw. This is not how this would work in basketball, though, because this person would actually get their first 2 free throws, and then this person would also have 2 most likely free throws. But whatever. We're going to pretend like this is how basketball works. So here we go. So in this question here, it's basically we want to know that what is the probability that one or the other will make a free throw. So that word or here should be making you think about the addition rule. So that means that the probability of A or B is equal to the probability of A. We know or is that. A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Well, now we actually know that the probability of A and B with independent events is actually the probability of A times the, oops, didn't mean to open that up yet, times the probability of B. So here we're talking about two different people. So technically we can consider that their free throw situations or abilities to shoot a free throw are independent events. So here the probability of either one of them is going to be equal to the probability. So again, the probability of either one is going to be equal to each one's individual probabilities added together, subtracted by their probabilities multiplied together, because that would give us the probability of both. So here I want the probability of Joel or Rico making it. So the probability of A is going to be the probability of Joel making it. So the probability of Joel making it is 32 out of 50. Added to the probability that Rico's made it. So Rico's made 42 out of 48. So that's 42 over 48. So you can see why they chose Rico. But then I have to subtract away the probability that they both make it, which is 32 over 50 times 42 over 48. So when we go to solve here, this actually becomes 32 over 50 plus 42 over 48 minus this together simplifies to 14 over 25. So when you add and subtract there, you get a decimal of about 0.955. So there's like a 95.5% chance that one of them will make that free throw there to win the game. All right, so I hope that is helpful in thinking about how independent events work and the different things that you could do with independent events, particularly when you add that addition rule back in, and then thinking about these tables. Now notice these tables were different this time. The denominator was always the same because we were comparing things out of the total, right? We weren't comparing things given other things. And that's why we weren't using the conditional probability rule. All right, so the homework for this is going to be page 305, 306, and 307. Except, hold on one sec. Number 10 is always bizarre and it upsets people. You can look at number 10, but don't stress about number 10 on page 307. Because I haven't looked at it enough to give a definitive statement, and I have the addition rule written here, but then I also have something with conditional probability written here, and I don't know what that is for. Huh, I don't even know what. Oh, it's a different problem. No, number 10, you should be fine. All right, so that should be it there, and then what we'll do on Monday is we'll meet together as a Zoom class. We'll go over those questions and we will do what are called conditional probability tables. And they're interesting and a little bit challenging, but not too challenging. So again, and we'll also go over some of the Delta math questions. So our lesson on Monday will not be in the Walsh book, so I'll post that file beforehand when I make it this weekend, but we are going to be doing something a little bit different for our last lesson just because there's some probability stuff that's not covered in the Walsh book that I want us to get to that you need to know. So that's it for now. Again, that homework was on pages 3. Sorry, close my book. pages 305 to 307. So Monday we'll go over 305 to 307 and do our last lesson. At Tuesday you'll have a Delta Math, and then that'll be it kind of for this stuff. But stay tuned. All right, I'll talk to y'all soon. Bye.